and the recordings will be made available to the public within 1 week of each webinar. For those of you who've been joining these webinars in the past, you will know this drill. We'd like to ask just a few questions with a Zoom poll before we get started with today's program. First question, what role best describes you? Feel free to complete this poll. Are you an engineer, a planner, a researcher, a consultant, a policymaker, or maybe something that we haven't explicitly listed? Our second question, what industry sector do you work in? Is it public sector, private sector, nonprofit, academia, or something else? And the third and final question, how long have you worked in the field? Less than 5 years, 6 to 10 years, 11 to 15 years, 16 to 20 years, 21 to 25 years, or 26 years and more? We're seeing great participation rates. Give it just a couple more seconds and then close the poll. Fantastic. As you can see, we have a lot of engineers and planners here joining us today, but also planners or researchers, consultants, and others. The industry sector that many of you work in is public and private. We really appreciate that because we will be showcasing public-private partnership and how that translated into successful deployments here in Utah. And a good representative sampling of folks all across the spectrum when it comes to years into the profession. So thank you for taking the poll with us today, and we'll go ahead and move to the next steps. UDOT has deployed connected vehicle technology in multiple ways on our roadways. Today's webinar will highlight the deployment process and lessons learned from deploying V2X systems along roadways and in vehicles. Our speakers today will discuss installation and testing of the roadside and onboard systems and the approach to system maintenance. In addition, speakers will discuss the generation of intersection MAP messages and the use of security certificates on those devices to protect the transmission of data over a V2X system. If you have any questions throughout today's program, please feel free to submit them in the Q&A. An icon is located at the bottom of your screen. If we are unable to answer all questions today, we will follow up with you directly via email afterwards. Let's move to our first presenter. For those of you who have not gotten the pleasure of meeting Leonard, Blaine is the Transportation Technology Manager at UDOT. In this role, he leads the planning and deployment of connected automated vehicle technology. He has chaired the American Association of State Highway and Transportation Officials Connected and Automated Vehicle Working Group, and he's also led the SPAT Challenge Tactical Working Group. He's co-chair of the AASHTO Technology Subcommittee. Prior to joining UDOT, Blaine spent 20 years in the consulting engineering business. He has a bachelor and master's of science degree in civil engineering, both from the University of Utah. We look forward to hearing from the person overseeing Utah's Connected program. Blaine.
Thank you, Muriel. Appreciate the kind introduction, and excited to be here today. Let me get my screen up. So we're excited about the Utah Connected program that we've been working on for a number of years now, and are excited to have all of you here with us today. I want to first offer some thanks. I want to thank the Federal Highway Administration, part of the USDOT for awarding us an ATC MTD grant that enabled us to do many of the things you'll see today. Appreciate their grants team in DC and their local FHWA office who worked with us as we worked through this process and made changes and executed these programs, hopefully successfully. These webinars are brought to you by the ATC MTD funding that we've received. If you're interested in the ATC MTD program and our particular grant, we talked about that in webinar 1, and we would invite you to go back and pull up that webinar and take a look. I also want to thank Muriel Sociamal and her team at X Factor, who have organized these webinars and kept us all on task, helped us prepare, and have blasted you with all kinds of emails. That's why you're all able to be here today, is because of her team's hard work. I want to thank today's presenters. We've got people from UDOT, people from our consultant Panasonic, and people from our consultant Narwhal group. Panasonic and Narwhal does all the real nitty-gritty work here in our deployments, and they have some really useful and detailed information to share with you today, and we're excited about that. I also want to thank all of you today who've joined us on this webinar or may watch this webinar later and on past and future webinars. We've got over 150 of you today. That's why we're here, is to share with you. And so that brings me to our webinar goals. Muriel talked about these just a little bit. Much of what we know and have been able to accomplish here in Utah is because of things we learned from other colleagues around the states over the last 10 years or so. And so we want to promote more information sharing because we think that's really important. We want to share with you what we've done, some challenges we've had, the lessons we've learned, so that you don't have to reinvent the wheel and make some of the same mistakes we did. We want to foster collaboration between all of us. We're all in sort of a new area here, and we want to be able to work together and move forward together. And we want to encourage all of you who have or maybe have not yet deployed some of these technologies to do so. Our transportation technology group has a couple of primary goals. Safety, of course, is the first one, and that lines up well with our agency's goal of zero crashes, injuries, and fatalities here at UDOT. And mobility is our secondary goal, to optimize mobility using these systems. As part of those two major goals, we want to achieve full situational awareness, i.e., we want to know what's going on our network around the state at all time and in real time. And that's kind of where we're headed with some of these technologies we talk about on these webinars. Secondly, from a connected vehicle standpoint, we want to be ready when the automakers start putting vehicles off their assembly line that have connected vehicle technology on them. We want to be ready to talk to them the day they roll into our highway. So we're working hard to get to that point. We want to encourage all of you to do the same thing. And by sharing, we hope to encourage broad deployment in lots of other places, which will in turn encourage the automakers to move forward. Well, as Muriel indicated earlier, deploying connected vehicle technology is really the topic today. We've talked about some general overviews of our system and what we've done in webinar 1 and webinar 2. We talked about some of our applications and our data platform and our data sharing. Today, we want to get very specific about what and how we've deployed. And we hope that this will be very informative to you. Here up front, I want to talk a little bit about how we decided to deploy. If you've been on a couple of the other webinars, you've seen this map. This is a snapshot of most of our roadside unit deployments in northern Utah. There's a few that are off this map and a few that are not shown here, but this is the bulk of our deployments, about 350 roadside units in the state of Utah. We started with this one right here on Redwood Road. Redwood Road is a multi-lane arterial on the west side of Salt Lake County, and that's where we started our deployments before we had this ATC MTD grant back in 2015 or so. And how did we get there? How did we choose that road? And how did we decide what to do there? Well, we started with a brainstorming session. We gathered a group of us together and we spent essentially all day hammering through an understanding of connected vehicle technology and how we might use it. And as we worked through a variety of applications that we might deploy here, looking for something that would bring us short-term value on a small scale, because we were starting small, we came up with transit signal priority. And so then we formed a partnership with Utah Transit Authority, our transit agency here in the populated part of northern Utah, and they agreed to work with us on this. Now, I have to note, we didn't decide to do transit signal priority and then look around for a technology to do that with. There are lots of different ways to do transit signal priority. We did the opposite. We were looking for a way to deploy V2X technology. At this point in time, it was DSRC, and looking for an application that would be useful there. And so transit signal priority is a vehicle, a means to an end, if you will, for us to deploy, at that time, DSRC technology and understand how it works and get benefit from it to justify the expense of deployment. So that's where that came from. Then we started looking around at where we should do this. We started by asking questions of our transit agency partner, UTA. Where do you have bus routes that are challenged in keeping their schedule? And they gave us a list of several routes that had schedule adherence problems. How can we help them get those back on schedule with TSP was the concept. As we looked at those, we looked at the corridors to determine which ones had other characteristics that were useful to us. We wanted a corridor with a reasonable amount of traffic so that we could be looking at other kinds of applications in the longer term, but we wanted a corridor that we could experiment on, if you will. A Redwood Road at the very north end has a fairly small traffic volume, and we could deploy a DSRC unit on one or two intersections up there. And if we caused a problem with the signal and it went into flash or whatever, which happened a few times, we weren't impacting a lot of people. Towards the south end of the corridor, we had higher traffic volumes, and we could expand that direction once we got a little more confidence with what we were doing. Redwood Road also was convenient for us because it was fairly close to our office. And so we selected Redwood Road because of those criteria. We then worked with UTA to identify which buses would operate on that corridor. This corridor has about, in our initial installation, had about 25 roadside unit installations. We started with 3 buses, and then we expanded later to 10 buses. That was a bit of a challenge because the buses aren't dedicated to a particular corridor. So we had to keep working with UTA to keep them having those buses run on this corridor when it's possible. But we identified buses that were conducive to deployment. And then we moved ahead to develop the software to do this. We're heavily involved in the Connected Vehicle Pooled Fund study with a bunch of other states around the country. And at the time we were having this discussion and getting ready to deploy, the Pooled Fund study had developed a system called MITS, Multimodal Intelligent Traffic Signal Systems, which was developed under contract of the Pooled Fund study by Larry Head at the University of Arizona. And we started with that software and then modified from there. So we didn't have to start from scratch, and we could learn from Larry and the other members of the Pooled Fund who had been working on this project to be able to move forward. After we got the software underway, then we identified, purchased, and tested DSRC, RSUs, and OBUs, and worked through that process of understanding how they work. We started with 4 different brands of hardware, actually, because we naively believed that they were interoperable, and in that day they weren't. And we also wanted to make sure we had some variety in our system. And we did system design and software design based on the fact that we were using multiple hardware platforms. We installed and integrated and tested and tweaked, and then tweaked some more, and then tweaked some more, and then tweaked some more on that deployment. As we moved forward that installation was completed in 2017. By 2019, we had this ATC MTD grant, and we started looking at other applications. We selected the curve speed warning application. And as we looked at crash data in the state of Utah on state roads, we identified corridors that had a higher incidence of curve-related crashes on them. And then we sort of down selected from there. And one of the first corridors we selected was Big Cottonwood Canyon. I've got a photo there of the notorious S curve in that canyon. And then we also selected some freeway interchanges in the valley that were fairly close to us that have sharp curves. And so again, we looked at corridors that met our needs, had acceptable characteristics and locations that were workable for us. Again, we needed some vehicles to run on these corridors. In this case, we selected a handful of fleet vehicles owned by UDOT, maintenance vehicles and things that frequent these locations so that we could equip those. We developed software. Panasonic did much of this work. And then identified, purchased, installed, and integrated the software on the hardware and tested it and tweaked it. And we're still doing that, testing and tweaking this particular application. We did something very similar with another application, spot weather impact warning. Again, we looked at corridors that had high incidence of weather-related crashes and ended up selecting Interstate 80, which is a steep canyon freeway segment that goes from Salt Lake City up towards Park City and then heads in towards Wyoming. And we have a lot of weather challenges on this fairly steep, windy road, and it made a good corridor for this application. We looked at additional TSP applications, and there are a number of them. I highlight just two in this case. The University Parkway, which is a bus rapid transit route known as the Utah Valley Express, or UVX, which was deployed in 2019. And under this grant, this ATC-MTD grant, we've recently completed State Street in Utah County, which is the UTA Route 850. And I've encompassed that in a long red box there. So again, we looked for characteristics that made sense for additional TSP applications. We also deployed preemption for our snow plows when they're actively plowing snow. And again, a number of corridors were selected for that. I've highlighted State Route 92 in Utah County because that was one that was done with the ATC-MTD funding last year so that we could improve the plowing operations. And we've discovered that providing preemption for our snow plows on some of these routes can significantly reduce their plowing time, in some cases cutting it in half, because they can move through efficiently these intersections without having to stop, and it just keeps them rolling. Another application that we've recently deployed is vehicle insights in an urban environment. We were interested in learning as much as we could out of the basic safety messages that fleet vehicles will send to us as they move around. We partnered with the city known as Orem in Utah County, a great partner there, developing what we have come to call an enclave, where we equipped every intersection in the city, some of which belong to us, some of which belong to the city, and over 100 fleet vehicles belonging to Orem City, so that we can watch those movements and learn about the movement of those vehicles and what insights we can get from them. We also enabled emergency vehicle preemption in that particular deployment. So as you can see here, each of the places we've deployed came about because we were looking for a specific application and where to best deploy it. And we thought through that process that I walked through on the first couple of slides here about how we go ahead to do that. So as we've done these deployments, and others today will get into the details of physically how we do that, as we planned and organized these deployments, there's a series of lessons that I think we've learned through doing this that I'd like to share. First of all, we started very small and then scaled up. And we think that's the right way to do this. Start small because there's a learning curve involved here. Experiment with a limited number of intersections, learn how the hardware works, learn how you get it going. And then once you do that and measure benefit, which we've done from our TSP and our preemption, and then scale up from there. As we did, find use cases that bring early small scale benefits. That Redwood Road deployment was fairly small. There was a lot of blood, sweat, and tears involved in getting that deployed. Once we got it deployed, we measured significant benefits in schedule adherence for those transit buses and narrowing the variance of their schedule by doing that. And so that's a great lesson, we think, that find a use case that can bring you some early benefits on a small scale. And then again, you can scale up from that. And we're learning that with the vehicle insights in the Orem area from our basic safety messages. What can we learn from that, and how do we next deploy that? As you deploy roadside units on corridors, those corridors need to be ready. You can't just take any corridor. The corridor needs to be prepared and capable of supporting the information that the roadside unit will broadcast. And so one of the first steps that we had to do, and that all of you need to do as you deploy, is to evaluate your traffic signal systems and improve those where needed, improve timing, make sure there's adequate backhaul from those locations. Those are all important. If you have old, relatively old signal controllers, they will not provide the SPAT data information that is needed to populate the SPAT message and broadcast it with the RSU. The beauty of this is, as you start to get ready to deploy V2X, or maybe you're not quite ready to do that, you can evaluate and improve your signal systems, and that will prepare you, but it will also provide a lot of other benefits from other users of the corridor. So it's a money well spent, if you will, in lots of respects. As you move through this, I will just note that the Connected Vehicle Pool Fund study has created a connected intersections guidance document. And here's a link for that. They've created a number of other documents as well, but this one in particular will help you as you walk through how to deploy on a corridor. All of the steps, there are checklists, there's a lot of information and a lot of references. And we wish we would have had that in 2015 when we started to plan. And so we've tried to put some of our input into that document as the Pool Fund has developed it so that it can be useful for all of you. V2X systems have matured significantly over the past decade. We had a lot of trouble with early systems. There was a lot of work in making them operate and talk to each other, and systems have matured significantly. If you've deployed before and you've kind of given up because it was a little too hard, I recommend you jump back in. Things are easier and more interoperable now. I won't say they're perfect yet. I won't say they're fully easy yet. But they're easier than they were, and there's a lot of improvements that have happened. There are a significant number of standards and resources that have been developed really just within the last 3 years that can help you. I've mentioned the Connected Vehicle Pool Fund study and at least one of their reports. There are several others. SAE and ITE, funded by the US DOT, has developed the Connected Intersections Implementation Guide, which is CTI 4501. That's currently being revised again, but this document is very useful as it stands. 5GAA is developing a day one deployment guide, which will be issued later this fall, that will have a lot of good information for our roadside deployments. And there are many others. This is just a sampling. Another lesson that we learned is that procurement takes time. To write a specification, issue an RFP, get the equipment, make sure it meets all your requirements, get it delivered in enough quantity to be able to do what you need to do. All of this takes some time. And it was a little harder than we thought to walk through that. Most of us as public agencies have fairly complicated and specific procurement processes we have to walk through. This is equipment that you may have not ever ordered before, and so there's some extra steps involved. But that was one of the lessons we took out of all of this. CV2X broadcast, connected vehicle technology, is a licensed spectrum that's operated by the FCC. And to install and operate these units, you need to have permits from the FCC. The FCC is currently working on, as you may have heard, new rules for how to deploy and permit CV2X roadside units and onboard units. And in the interim, while they're building those rules, you need a waiver to deploy these. FCC issued a waiver to two agencies, Utah and Virginia, and a number of private sector companies, including Panasonic, back in April. And last week, issued a waiver for 17 other jurisdictions around the country. It took a long time for that to happen. If you're not one of those agencies who has a waiver, I would encourage you to apply for one immediately. Even if you don't plan to deploy for a while, we don't know how long going forward the FCC will take to approve waivers. These rounds took a long time, and I would encourage you to apply for one. If you don't know how to do that, get in touch with me. I've got a template you could follow where you could jump in and get this moving. It's a step that you just need to do at some point, and the sooner you can get it done, the better off we all are. And finally, you just need to start. That's a lesson we learned early on. We started when these technologies were still immature, and we spent a lot of time learning and a lot of time making mistakes and correcting those mistakes. But even now, with more mature equipment, this process takes some time. I would encourage you to start now. You don't have to move quickly. You don't have to move large, but start now so that you can get on that learning curve and move ahead. So those are some of the lessons that we've learned over the past 8 or 10 years deploying, and we've certainly learned again and again through this ATC MTD grant project, and are continuing to learn as we move forward. So I will just offer those to you. If you have questions about anything I've talked about, submit those in the Q&A. We'll have some time at the end of the webinar today where we can respond to those. And with that, I will stop my slide sharing and we can move on to the next presenter. Thank you.
Fantastic, Blaine. Thank you so much. And we do have a couple questions for you. So we will make a note of those and ask you at the end of the webinar. Now we turn to our next presenter, Scott Tuttle. Scott is the Customer Delivery Manager within the Deployment Solutions Organization of Cirrus by Panasonic. He leads a team of engineers responsible for designing and delivering edge solutions to the field. With 500 plus devices deployed to date across Utah, Colorado, Georgia, and even Texas, Scott has over 10 years of experience working on large-scale systems, engineering projects, and has been working for 2 years on connected vehicles. Prior to joining Panasonic, Scott worked in the aerospace and defense industry, supporting various projects in the areas of systems integration, research and design, business development, and operations analysis. Scott has a Master of Science degree in Systems, Architecture, and Engineering from the University of Southern California, and a Bachelor of Science degree in Aerospace Engineering. Please welcome Scott.
Thanks, Mariel. All right, I'm excited to share with you all today a high-level summary of what our process looks like for deploying connected vehicle systems to Utah. Deploying connected vehicle technology can be tricky since every fleet owner or infrastructure owner operator is a little bit different. They all have different needs, they have different systems that are already in place, and different ways they manage their infrastructure or operate their vehicles. So with all this variability, it's really important to spend time before you're in the field to understand the context of a particular deployment. So for all the deployments that we've partnered with UDOT on so far, we've followed a 3-phase process. Those 3 phases are deployment planning, installation execution, and each of these phases concludes with a deliverable report that clearly identifies what decisions were made, to help make sure that all of the stakeholders are on the same page and everyone's needs are being met. Once that installation is complete, these systems are transitioned into an operations and maintenance phase, where we continue to monitor and service those edge devices to ensure operations. By following this standardized process, it really establishes for us a repeatable method for performing large-scale deployments that we're confident are high quality and as affordable as can be. So over the course of this presentation, I'll touch on just a few of these key activities from each of these phases to highlight what each of them looks like, so you all have a sense of what's involved in deploying CV solutions. So deployment planning can be described really as the why, the what, and the where. During deployment planning, we work alongside UDOT, the fleet owners, and the local infrastructure owner-operators to really understand why we should be deploying CV technology to their roadways and to their vehicles in the first place. What are the most important problems or challenges that they're facing? You heard from Blaine just moments ago what many of those were in the context of some of our northern Utah deployments. Once we understand why we want to deploy CV technology and what solutions are available to help, we can begin to select the roadway locations and the vehicles that we should target for the deployment. Ultimately, at the end of deployment, the deployment planning phase, we want to establish a few artifacts. So a clear description of what those objectives are, a vehicle list of the vehicles that will receive the onboard equipment, and a site list and map that represent the locations where the CV connected vehicle equipment and roadside equipment should be installed. So there's of course a wide range of capabilities that connected vehicles can offer. Throughout the UDOT grant, we've really focused on a few important areas. So one is basic safety, traveler information, and then CIPT, which is connected intersection preferential treatment. I'll touch on what each one of these is at a high level. So basic safety, any information about basic safety can really be collected from any vehicle that is equipped with an OBU, as long as it's broadcasting on the J2735 standard basic safety message, or BSM. By collecting this anonymous data, users can perform data analytics, they can generate visualizations, things that help us better understand what's happening on the roadways. We can identify crashes or other incidents like a stalled vehicle, or we can infer weather conditions on the road by using information from the basic safety messages like ambient temperature, windshield wiper status, or ABS activation. Traveler information allows us to deliver important messages to drivers directly in the vehicle through some form of in-vehicle display. So this could be weather warnings, an advised speed of a sharp curve ahead, or just a heads up that there's road work ahead of the driver. CIPT is a category that covers a variety of the different use cases involved with priority and preemption. So this is where a designated vehicle can make requests to an intersection under certain conditions that help them move through that intersection more quickly. So I'd like to pause here and poll the audience. I'll give the team a moment to bring that up, but the question will be, if you were starting a new connected vehicle deployment, which of these solution types would you be most interested in implementing?
My apologies, Scott. We're trying to pull it up.
No problem.
We may need to relaunch. If you don't mind continuing with your presentation, we'll
Nope.
try and get that worked out.
Okay, no problem at all.
Thanks.
So having talked about some of those capabilities, and once we know what those capabilities are that we're looking to implement, we start researching the region and the fleets that are going to be involved in this deployment project. There are a lot of different resources that are available to us that we can pull from in order to do this research. On the vehicle side, this includes things like route maps, so snow removal routes, bus routes, or major freight corridors. We also look at centralized fleet locations like bus depots, snowplow sheds, fire stations, medical centers. And then of course, we also pull information about the vehicles themselves, vehicle lists, to get details about those vehicles. On the roadside, we might research crash statistics to identify high-risk turns. And on intersection, for intersection applications, We'll pull from databases like ATSPM, which is UDOT's automated traffic signal performance measures database. And then for standard roadside deployments, we'll work with the IOs and UDOT to understand where existing infrastructure is located already. And that's really to keep costs down. We always target deployment locations where there's already power and network connectivity available. So we use all this information to come up with a target list of vehicles and roadside sites. And we often develop a set of deployment maps which show how these routes and key locations for fleets overlay against roadside deployment sites we've selected. And this just gives us a really comprehensive picture of the overall deployment, what it will look like, and make sure that those deployment objectives that we established earlier are being met.
Okay, Scott,
yeah.
I apologize. We are ready to launch if you are.
Okay, let's do it before we go to the next section. Yeah.
Perfect. There we go.
The poll is, if you were starting a new connected vehicle deployment, which of the solution types would you be most interested in implementing? Would it be one of the three we covered here, basic safety, traveler information, or connected intersection preferential treatment, or some other application that we didn't list? All right, a roughly even spread there. A tie for basic safety and connected intersection preferential treatment, but also plenty of responses for traveler information as well. Thank you for participating. All right, so the next phase of the process is installation planning. This is where we dive into the how of the deployment. We really want to understand the details of the installation, like what equipment will be installed, how will the equipment be integrated with the vehicle or the existing infrastructure, how should the devices be configured based on the decisions we made in the deployment plan. So I'll just touch on a few of those key activities for both the vehicle and roadside installation planning activity. I would say the majority of the work involved in the deployment process occurs during the installation planning phase, because this is really where we investigate all that unique variability across the vehicles and the locations. The diagram on the right-hand side here is an example of how the onboard equipment has been integrated with the UDOT snowplows in one of our recent deployments. The boxes in yellow represent the connected vehicle equipment that's being installed, and all the multicolored lines show the different ways that that equipment interfaces with the plow and the other supporting services for that OBE. When planning an installation, we work very closely with the fleet owners to determine how to properly connect to power, what type of diagnostic port on the vehicle we need to use for the CAN interface. For vehicles getting priority and preemption, we also define the CIPT triggering interface and associated logic. So UDOT doesn't want vehicles requesting priority and preemption at just any time, since this can be very disruptive to the regular and planned traffic operations. So instead, we define certain conditions that trigger the system to make these requests. In the example of the snowplow, the salt spreader system needs to be activated. This way, the snowplows are only requesting preemption while they were actively treating the roadways. All of the OBUs have a set of GPIOs that we can leverage to make physical connections to different systems on the vehicle. So there's really a lot of flexibility in how we can set up that triggering logic across all the different vehicle types. For equipment installation, the physical equipment placement and cable routing is another key element of the planning activity. So we want to make sure that the antennas are placed in locations that offer a good field of view, but also don't interfere with existing antennas or other equipment on the vehicle. There are many different locations that we can install the OBU as well, depending on the vehicle configuration and availability of space. Some larger vehicles like transit buses have equipment cabinets, which is really nice, but oftentimes we're looking for a place to tuck the OBU away under a seat, under the dash. And we have really modular cable harness designs that give us a lot of flexibility also in where and how we install this equipment. But it's always best to plan this out as much as we can before the installation so that our team of technicians doesn't have to figure this out along the way when we're doing dozens of vehicle installations at a time on site. In most cases, especially with light duty vehicles, we've performed enough installations to date that generally we know what to expect and how to do these installations. But for some of our more complicated vehicles like snowplows or fire engines, we will sometimes perform vehicle assessments. So in this case, we'll send an engineer out, they'll travel to the fleet and they'll gather information about the vehicle that will help with our designs. Sometimes if the installation is especially complex or novel, we'll also perform what we call as a first article installation. It's just a one-off installation on one of the vehicles in the deployment, sort of like a prototype, ahead of performing that installation on the rest of the vehicles of that type in the fleet. And this can be really beneficial because one, it gives our team firsthand experience that will help us make all of those follow-on installations run more smoothly. But it also gives our fleet owners a working system that they can use to make sure that the system is meeting their needs. Finally, we also define how all of the devices will be configured, what communication channels will be used, what security certificates should be applied, and then what permissions, in the case of priority and preemption, will be granted to that vehicle if applicable. So all of this information is compiled into an installation plan and deliverable, which gets reviewed by UDOT and other stakeholders before we move forward. So this is just some photos here of onboard equipment installed on the snowplow, like that diagram we saw in the last slide, just as an example. Since inside the cab on a snowplow, things can get very wet during a snowstorm, tracking snow in and out. In this case, we mounted the OBU on the wall behind the driver's seat instead of some of our other usual locations that were at risk of getting the device wet. We also have a few options for mounting the V2X GNSS antenna, which is the photo just to the right. Sometimes we'll stud mount this antenna and run the cabling directly into the cab, running that wiring behind the trim panels. Other times we'll use an adhesive to mount the antenna and then run the cables through a wire loom into an existing vehicle penetration, which is what we did here. The LTE antenna in the photo below, this we simply tucked behind the dash since there was plenty of space in the plow. That gave us good LTE reception through that large windshield and also kept the antenna out of the way. In all cases, our installation techs do a really good job of running wiring behind panels and otherwise out of sight so that these installations always have a clean look and the equipment looks like it was meant to be there from the start. The devices on the right side of the slide, that's sort of optional equipment that's dependent on the use case of the vehicle. So the top device is the OBP or onboard processor. You'll hear more about that from Narwhal later on in the webinar. And then we also sometimes install human machine interfaces just in those in-vehicle displays, which we have a number of options on if that vehicle should be benefiting from those travel information messages. Moving on to the roadside, the diagram here is for a connected intersection installation, as opposed to a standard roadside site, which would look a little bit different. So the yellow boxes here also represent the new equipment to be installed. Integration into the existing infrastructure is always the first thing that we try to determine. Typically, we'll also send a team out for the roadside that will perform a site survey. We'll confirm that power and network connectivity are available. We'll also make sure there's enough capacity in the cabinet for new equipment. So is there rack space in the cabinet? Are there power receptacles available? Is there an open detector channel if we're installing an SCM? And then when planning for the physical installation of the RSU, there are guidelines we set for things like height and mounting method that are taken into account. And although it hasn't been too much of a problem in Utah, we have observed issues with electrical surges from lightning strikes causing damage to the roadside equipment as well. So we put a lot of effort into improving our bonding and grounding designs at the poles to reduce this risk. Device configuration at the roadside, like the onboard equipment, it's really important, but beyond just configuring the RSU, Connected intersections require configuration of the signal command module, or SCM. It's another device you'll hear more about from Narwhal, as well as the traffic signal controller inside of the cabinet. All these things need to be programmed for each intersection, so that's something we plan for too. Again, all of this information goes into the installation plan alongside our standard processes and procedures that we've developed over time that help us establish that efficient, repeatable installation process. These photos here, again, are just an example of a connected intersection installation. The left-hand side, of course, shows the RSU mounted on a pole with its mounting assembly components. And then on the right-hand side, you see all of the devices that reside inside of the cabinet, including the SCM, the power supply, surge suppressor, and all the network equipment. Finally, installation execution. This is simply us performing the field work itself, verifying that everything functions as intended, and then gathering the information and generating the reports to document all the work that was done for the as-built system. One thing I'll highlight about this phase in particular is the importance of the full team really being required to get this done. Panasonic partners with companies like Narwhal, who bring really important expertise, and a crew of qualified engineers and technicians who can get the work done in the field in accordance with local guidelines and regulations. And similarly, on the vehicle side, we partner with companies who staff certified automotive technicians so that all the work is being done to a level of quality that UDOT and our other stakeholders expect. There's also a lot of coordination and logistics that go into the field installation itself. So the continued support, especially during this phase from UDOT, the fleet owners, and the IOOs is really critical. And I think it's that team approach across public and private organizations that has made these deployments successful in UDOT so far. During the field deployment itself, we use a long list of tools. Many of them have been developed in-house over time as different needs have risen. So these tools support all kinds of activities in the installation execution phase, like device configuration, testing, asset management, work tracking. For the sake of time, I'm just going to touch on a couple of these today, but I'm happy to provide additional details if anyone is interested or would like to request more information after the webinar. One of the most important tools for our deployments is the Computerized Maintenance Management System, or CMMS. So this is the platform that we use for tracking and maintaining the field assets and the related field work that we perform. We use the system not just during the maintenance phase of the system lifecycle, but right from the start during the deployments, so that all of the information about devices, locations, configurations applied can all be loaded into the system at the time of installation. The tool really has two parts. One is SoftReng, which is more of the front-end user interface, and then Maximo, which is the database. During all the field work, the technicians carry a tablet with them that has all the work orders for every installation to be performed. We've generated, by this time, we've generated automatically all of these work orders using those target vehicle lists and site lists and all the associated information we've gathered from the planning phases. And this really helps the technicians to know what work needs to be performed, what devices should be deployed to which vehicles or which locations. We can scan devices to get their serial number and other information from the barcode, or enter information manually right on site on the tablet into the work order, so that there's that traceability into, for example, which serial number was put into which vehicle or which location, and which systems successfully passed their verification tests. This tool is really customizable, so we've been able to develop a lot of automation that helps us scale this process effectively. Next, I'll talk about the CIPT Configuration Manager. So this is the tool that we use to define and manage priority and preemption roles and permissions. The system's cloud-based, so that allows the OBU to download the correct profile for a specific vehicle based on the VIN that it reads from the CAN interface. And we can update these profiles, all the information like names, roles, permissions, for either a single vehicle or for a full fleet of vehicles remotely, so we don't have to go out and physically touch the equipment to make these changes. You can also simply toggle the application on or off in case things change over time and a fleet owner or IO decides they don't want to permit CIPT permissions for a particular vehicle anymore. We've incorporated a lot of automation into this tool as well, which allows us to do things like bulk load profiles for a full fleet all at once, which is really important and valuable when you're doing deployments of 100 vehicles at a time. And then the last tool I'll cover is our mobile testing platform. This tool we take with us on every single vehicle deployment to verify that the installed equipment is working. The tool includes a computer, a tablet, monitor, and it also has an RSU inside, all in a protected travel case. And having that RSU on site where we're doing the vehicle installations lets us test the transmission of the V2X messages coming from the OBU that we just installed. So we can check for that the OBU is functioning without having to take it on a drive test out past some RSU on the road. The tool shows message contents as well, like VIN, vehicle role, SRM timestamp, so we can confirm the OBU is configured properly. And it also lets you test information like test for information like transmission state or wiper status or turn signal, things that are included in the BSM, which would indicate that the CAN integration is functioning as well. The tool also displays information about OBU health over an LTE connection. So there's a lot of information really that the technicians can pull from to help troubleshoot an installation in case a verification test fails, and really so that we can resolve it on the spot. And this makes the tool invaluable because we can confirm for the vehicle owner that the system is working before we give that vehicle back to the driver. So that covers the three-phase deployment process. But as I mentioned earlier, once we've completed the installation, we continue to provide support to these systems to make sure the deployment as a whole continues performing throughout the sustainment phase of the project. So our operations and maintenance services really break down into three categories: system monitoring, system management, and maintenance services. So we use tools like Cirrus RSU Manager, which we spoke about in the last webinar, to monitor the health of our devices. In Utah, we have huge volumes of data coming back from these fielded devices, so we can track all kinds of things like health statistics and performance metrics. And we can also, we can view the data in aggregate, but also drill down into specific devices to see fault reports to really understand why maybe a particular site or vehicle isn't functioning. In addition to monitoring, we also support UDOT in managing these devices. So we provide real-time software tools and also service desk support. So a user can submit a ticket if they need help on anything or if they identify an issue with some device out in the field. Of course, sometimes these systems fail and can't be recovered remotely. So we also provide field maintenance services where we'll send a technician out to the device to troubleshoot and potentially replace that device. In order to do this, we make sure we have spare inventory available for replacements and the necessary team and subcontracts in place to go do that work on site. So I really appreciate the opportunity to share this information with you all. I hope it was a valuable summary of what the deployment process looks like. There are many details we couldn't cover in the time we have today. So if you were left wanting more on anything or have any particular questions, I'd like to offer up a way for any of you to reach out to our Panasonic Smart Mobility office. Tim Adams is our head of business development. So if you have any questions, here's his contact information. Feel free to reach out and he will put you in contact with the right person. Thank you.
Perfect. Thank you so much, Scott. We'll now turn to the Narwhal group. We have two presenters today representing the Narwhal group. The first is Jonny Turner. Jonny is a founding partner of the Narwhal group and is the program manager for the V2X systems with the company. He's responsible for all V2X activities, including new hardware and software research, design, development, system deployment, integration, systems testing, and maintenance. So he wears many hats. Jonny leads a talented team of engineers, technicians, and developers to provide emerging ITS solutions for real-world operational environments. Jonny has 23 years of experience in all areas of ITS and has a bachelor degree in electrical engineering from the University of Utah. He's also a licensed master electrician and serves as the company's contract qualifier in multiple states. Ralph Koeber is a senior electrical engineer with the Narwhal Group and involved in all aspects of V2X deployments. He's primarily responsible for the configuration, testing, and verification of equipment installation on these new V2X routes. He also is responsible for maintaining and troubleshooting existing installations. Ralph has a Bachelor of Science degree in electrical engineering from the University of Utah and is a licensed professional engineer. He also holds a master electrician license in multiple jurisdictions. With that, we'll go to Jonny and then Ralph.
Thanks, Muriel. Let me just get my slides up. All right, so Scott did a great job of covering the different elements of the deployments, and specifically at the intersections. And not all of the UDOT deployments are at intersections, as Blaine and Scott both discussed. But I wanted to dive into a couple of additional hardware, software elements that we've deployed here in Utah as we've started those deployments in 2015, as Blaine mentioned. And some of those are still out there today, and wanted to go into these different additional roadside and onboard equipment elements. So as Scott went through in really good detail, the hardware and software and system elements, you can see here the RSE, the roadside equipment, and the OBE, onboard equipment. We're going to hone in on two elements that may or may not be required for your deployment. We have both of these in our deployments for different reasons, and we'll go through those. I'll focus primarily on the roadside equipment, specifically the roadside processor signal command module, and Ralph will talk more about the OBE. So much like the architecture document or detail that Scott provided, we see that here are the primary elements that are happening at the roadside, and the SCM is one of those. So the SCM is a result of early deployments in the DSRC world, where, like Blaine said, there were 4 different manufacturers that we were working with and trying to port MITS software over to and stand up the MITS program. And we found some ways to do that. MITS originally was provided through the OSADP to be loaded on a vendor-specific DSRC platform on the OBU and the RSU, and we wanted to be able to run that software on any hardware platform, and found that the best way to do that would be to have a roadside processor running that software. And through that testing, we found that MITS had some limitations in that it needed to take control of the signal controller to do all the traffic signal timing. And that was just something that we can work with the traffic signal timing group as coordination was running, and some other kind of institutional elements when it came to the traffic signal controllers. So when working with UDOT, we came up with the SCM, and you can see that in the right-hand picture a little closer, and it goes in the detector rack and interfaces with the detector rack and communicates with the controller through the BIU. So it's a 4-channel card, and it goes in, a 4-position slot, and it provides the ability to interface with the controller and the RSU. So here's just a list of the functions and capabilities of the SCM. And like I said, the primary element is to provide that interface between the RSU and the traffic signal controller, which wasn't available early on, but we found is still highly useful in implementing these systems and applications. So the primary use of the SCM is to provide a map visualizer, provide a way to view SPAT. So the TSCBM is what is output from the controllers in the UDOT system. There's a couple of different controller manufacturers, Q-Free and Econolite, that are used. and they output TSCBM. Those that are involved in the different committees are very familiar with that. And it receives those TSCBM messages and creates the actual SPAT messages. We also do RTCM broadcasts from the SCM, and then it also is involved with TSP and EVP, or as Scott said, CIPT applications. So the SRM and SSM messages are also in the mix there. And then it provides that electronic input to the controller via the detector rack. So the nice thing about the SCM was it provided a really good off-the-shelf piece of equipment to make the V2X technology useful, as Blaine mentioned, in getting a really good return on your investment out of the gate and be able to see some benefits from it. And the other benefit is that it can use pretty generic signal controllers, because it just uses detector inputs. The UDOT engineer specifically said, don't use the EVP slots, please use just regular detector slots, so that we can manage and create the logic in the controller and have the full control and capabilities that we can control the preemption and TSP elements. The other benefit is that it interfaces with RSUs that are standards-based very well through different messaging, immediate message forwarding, and things like that that are standard in RSUs that are really, off the shelf standard market RSUs. The other benefit is we can actually use 8 outputs, so we get a lot of flexibility in doing TSP or EVP or snow cloud preemption for different fleets. And one of the other great elements, and one of the reasons we went with a detector card type controller, was that it would allow the signal tech to walk up to an intersection, in the middle of the night. They get called out very frequently where there's a problem, something's not operating correctly, and it provided an interface for them to just pull the card and make sure that that's not the element that maybe is throwing the signal into flash or causing some problems with the controller, which can be reset later on. And it provides a very standard hardware device that they're familiar with. So the software interface of the SCM provides, like I said, that map visualizer, which you can see in the green, and the dots are the different map elements. You can see a couple of buses on that screen, and it provides a display of the different messaging elements. We're not going to go into all of the menus and items today, or in a lot of detail. That's going to be covered heavily in webinar number 4, how we do this configuration both in the SCM and the traffic signal controller, because they're a very complementary setup. So here you can see the map. You can also see the SPAT status, which is in the top right. And then finally, you can see the other J2735 message sets that are there. So when a vehicle comes into range of the RSU that's broadcasting, we'll see the BSM ID show up, and we can see some of the information. We've summarized some of the information from the BSM in the display here. Then we can also see the SRM, or the signal request message, that's coming from the vehicle that's running TSP or preemption. And then the signal status message, or SSM, is the response. And you can see that it's in response to the SRM request message. And in fact, this one shows rejected, and there's reasons for that that we'll talk about a little bit later on. I guess I'll go into that just slightly. So we can also make the lane level assignment. So we can discriminate by vehicle role. As you can see here, we have DOT, fire, ambulance, transit, so on and so forth, that are based on the standard vehicle roles. And then within there, we can do lane level discrimination of a vehicle role. So we can provide a EVP or preemption for eastbound in a very specific lane. This came in really handy on the UVX route, and also the recently installed Ogden express bus projects where there's dedicated bus lanes. So we only provide priority functionality in those dedicated bus lanes where they're there. So if a bus is in a general purpose lane and going through and meets the criteria for priority or preemption, we won't provide it and we'll actually reject that request. And so we can discriminate by lane, vehicle row, who's going to get those privileges, because there's an overall impact to the traffic signal timing and coordination every time there's a priority or preemption event. And so we just want to make sure that it's not a wide open request happening in any direction. And what we found is that the UDOT in this case, but also other agencies that are IOOs that are running traffic signal corridors, are more liberal with what they'll allow for priority when it's only requested under the right conditions versus just on all the time. And then finally, when the proper requests are made, we can see that there's a relay output that goes to the traffic signal controller. Like I said, this is just a really high level overview of the SCM, but and kind of a history of why it's there. But we'll go into it more in webinar number 4, and we can take a deep dive into a lot of those questions too during the Q&A in this meeting, and also webinar number 4. So with that, I'll pass the time over to Ralph. I think we actually have a poll, and then I'll pass the time over to Ralph to talk about the additional hardware that's on board. So we're just curious what industry the different participants are in. So what industry are you involved in? A transit agency, an automotive manufacturer, or OEM, DOT, or infrastructure owner and operator, or V2X manufacturer? I guess I should have asked for other, but this will do. So if you aren't one of those, I guess use your imagination and think what would be closest to yours. Thank you so much.
Fantastic. Thank you, Jonny. It looks like folks are taking your poll right now. Overwhelming majority of our participants today are from a DOT or the owner.
Great. Yeah, I can't see that on my display, but that's great.
We will show it here in just a minute. There we go.
Wow. Yeah, overwhelming majority.
Fantastic. Ralph, feel free to take it away.
Great. Thanks, Muriel. Let me get my slides up here. Okay, so I'm going to be talking about the vehicle side, the onboard processor specifically is what I'm going to be talking about. So here we have a kind of an architecture of what it looks like, what the equipment looks like on a bus. We have an onboard unit, of course, the OBU, and the OBU has antenna cables and an antenna that send and receive messages. They receive GPS. We also have an onboard processor called the OBP. The OBP interfaces with the bus, the network that's on the bus itself. The buses have UTA, Utah Transit Authority buses have a network on the bus that's connected by cellular network to their ground-based system for monitoring, tolling, or fares, and monitoring ridership and other information that they collect. The OBP interfaces with that and gets some information from the bus that we'll talk about in a minute here. Some of the OBPs are connected to the J1939 CAN bus on the bus. In other deployments where there is not a traditional full OBP that Scott talked about, the OBU is directly connected to the CAN bus, the J1939 CAN bus itself. Obviously, those two devices, the OBP and the OBU, are connected to the network on the bus by standard Ethernet cables. The UTA bus network, the information that we're really looking for to the OBP is the occupancy, how many riders are on the bus, the reliability, which is the lateness of the bus, and the eligibility, whether the bus is eligible for TSP if it's on a route that's eligible for TSP or not. In the case of the buses that to date, the occupancy threshold has been set to 0. That's partly due to the UTA network. Occupancy values are they're a little bit suspect, I guess. I'll say it that way. The reliability is the one that we really are looking for, and that indicates whether the bus is on time, late, critically late, et cetera. So for instance, if a bus is early, there's no need to provide any CIPT or TSP for the bus. The signal timing can remain as is. If the bus is on time, same thing. If the bus is late or critically late, then changing the timing of the signal is advantageous to getting the bus back on schedule. And the lateness value in terms of minutes or seconds of how late the bus is varies from route to route. So for an example, up to 3 minutes behind schedule may be considered on time. Once the bus is greater than 3 minutes late, then it would be considered late. And if it's more than 5 minutes late, that might be critically late. In either case, if the reliability is late or critically late, then the OBP and the OBU working together can request, we'll send an SRM message and request the CIPT or request a signal timing change in favor of the bus. Let's take a look at the snowplow architecture that's just similar. Snowplows, obviously, they get it, they're set up for preemption. It's the CIPT that UDOT gives them. We have an onboard unit here on the snowplow as well. This is a picture of our test vehicle, a Narwhal owned vehicle that has the equipment mounted in here for testing purposes. And again, an onboard processor. The difference that there's no onboard network on the snowplow, so we just have a voltage signal that comes from the spreader controller that tells the onboard processor it's time to send an SRM next time you're on a map. And we're connecting those vehicles to the J20 or the J1939 CAN bus as well. As I mentioned before, the spreader or the sander controller, when it's actively applying salt or sand to the roadways, that usually is occurring while the plow is down, then there's a voltage signal that goes out, and the onboard equipment will send a SRM requesting consideration for preemption at the next intersection it goes through. So the onboard processor, let's look at that a little bit more in detail. It provides an interface between the whatever the vehicle environment is, whether it's a voltage signal from the snowplow or it's an Ethernet network-based system from a bus. Provides an interface between that system and the OBU. We have software running on the OBP that provides us a couple of nice features, such as the ability to visualize map, SPAT. Those would be received over the airwaves from an RSU. So on the vehicle, we can see which maps are being received, the SPAT that's being received. We can see if the onboard equipment is receiving RTCM messages from an RSU. We see information about the signal request messages being sent to the roadside, and we see responses back in the form of signal status messages. Again, this is similar to the RSU that allows us to use off-the-shelf OBUs of different manufacturers and interface with them by using one piece of software on the OBP. It makes it easy to interface with different OBU manufacturers. Let me go back one here, sorry, forward. We also have the ability, if the OBUs support IFM, which is pretty basic, then the OBP functions with the OBU. So basically, we're using the OBUs as a radio, and the OBP is doing all the processing. It's also generating the BSM, it's generating the SRM, it's processing and reading the information of SSMs. And it also is, if we're broadcasting RTCM at a particular intersection, which UDOT is currently doing at a limited number of intersections, then the OBU will forward the RTCM messages to the OBP. And if the OBP is equipped with a advanced GPS or GNSS chip, then it can actually make the calculations to correct the location and create BSMs with DGNSS, so that the location is much more accurate than standard GNS or GPS allows us to have. So here's the onboard software the OBP provides. We can see a display of a map that's being received. This particular map is the Narwhal office. It's not actually even an intersection. We just created this one as a test, so we can drive our test vehicles in the parking lot here outside of our front door and make sure that things work. But we can see the map. We get a nice satellite view of that, and we can see the lanes and the nodes. We can also see, in this particular case, we were testing using the UTA bus algorithm. So we were feeding it simulated bus information about the reliability index. So this particular bus was late. It was running on a route that was eligible for TSP, and occupancy was 0. But as I mentioned before, the threshold for occupancy is typically set to 0. We can also see BSM information about the actual location of the vehicle, a timestamp, the speed and heading, some very basic information about that comes from the BSM. Those again would be forwarded over IFM to the OBU for broadcast. We can see the SPAT information, again, very basic. This is more of a technician tool. This user interface tool, but we can see which intersection we're receiving SPAT from and a timestamp. And we see also information about the SRM and the SSM SRM that's being generated by the OBP and broadcast by the OBU to the RSUs, and SSM information coming back. Again, this one was rejected because we did not have lane mapping set up in this test case for a transit vehicle. If we had set it up, it may have been processing or some other value there. So I mentioned that we have the capability through the OBP to accept RTCM messages and correct received GNSS messages and create DGNSS. So that's basically taking the GPS signal, which is accurate to around 1.5 meters, and create BSM messages that are accurate to somewhere in the 10-centimeter range. This is an example of a case where we set up a test vehicle that was receiving RTCM messages from a roadside unit and was processing the RTCM messages and correcting the GPS that was being received and creating a DGNS for BSMs. We plotted those BSM points, imported them into Google Earth, and this is a street level view. Well, on the left is a satellite view, an overhead view, and on the right is a street level view of the lines that connect the dots of the BSM. The blue line is the DGNSS, so the corrected location, and the red line is the GPS or the GNSS location received directly by the OBU itself. So we had 2 antennas on the vehicle. They were both mounted in the center of the vehicle, left and right, and one was slightly ahead of the other. And we can see that it looks like in the case of this, at this instance that this test was run, the received GPS without correction was drifting slightly to the right compared to the DGNS in the street view there. So summary of the operation, how this all works on the roadside. The roadside equipment that Jonny talked about, it's always broadcasting map and SPAT. The bus network provides a reliability and lateness threshold to the OBP. The OBP then sends that, well, when the bus enters a geographic map area, and the bus is later than whatever the threshold is, then the OBE, the onboard equipment, sends an SRM. The roadside equipment then receives that SRM and checks the SRM for the vehicle role and the lane that it's in. And if the programming on the roadside equipment says, okay, that type of vehicle in that lane gets some sort of CIPT, then it sends an SSM that says it's been requested or it's processing. If that vehicle is not programmed to have CIPT in that particular lane, then it will be rejected. If it is allowed to have CIPT, then the roadside processor or the SCM, the signal command module, activates the detector card relay when the vehicle role and the lane mapping match. And that the detector relay, once it's activated through the BIU and the SDLC, connects to the signal controller, and the signal controller has some programming, some custom programming in it, user programming with logic flags that activate either TSP or preemption depending on the vehicle type. And when the bus crosses when the vehicle crosses the stop bar or leaves the map boundary for any reason, then there's a cancel message that's sent on the SRM. An SRM containing the value cancel is sent, and the whole process of TSP stops. So for preemption on a snowplow, it's similar. The roadside equipment's broadcasting map and the OBE's broadcasting BSM. When the vehicle, an emergency vehicle or a snowplow, enters the map area and conditions are met, meaning for a snowplow, the spreader, sand or salt spreader is operating, or an emergency vehicle, the emergency lights are active, then the onboard equipment, meaning the onboard processor plus the OBU broadcast an SRM. And again, the roadside checks that and says the SCM on the roadside says, is that SRM coming from, it's a vehicle type, or it's a fire or a DOT vehicle. And my programming says that for that lane, that CIPT is allowed. And so that activates detector relays, which again goes to the signal controller through the detector rack and the BIU. And once the plow crosses the stop bar, or emergency vehicle crosses a stop bar or leaves the map, then there's a cancel message sent and the process stops. And that is it for my presentation, but that kind of only works if there's map messages. So I'm going to segue into Chuck Felice with maps, but I think we have a poll up next. And our last poll for the Narwhal group is, have you successfully deployed V2X? So for attendees, if you've successfully deployed V2X of any size, yes, no. And if you're not sure what V2X is, then there's an option for that as well. So it looks like the majority of people have not deployed V2X yet, but obviously you're interested in it. So we're glad to have you here for this webinar, and hopefully it's helpful. Thanks.
Thank you so much, Ralph. That was really informative, and we have a lot of questions for you. So let's go ahead and get to our next presenter for the day, and then we'll get into Q&A with our participants. So Chuck Felice is a project manager over software development and GIS at UDOT's Transportation Technology Group. He has been instrumental in UDOT's connected vehicle technology projects, specifically with software oversight and standardized message development. He is also engaged with connected vehicle standards development. Charles has more than 35 years of experience working in the software industry in both the private and public sectors. He has also worked in the civil engineering, aerial photography, and mapping industries. And with that, we'll turn to Chuck.
Okay. Can you see me, Muriel?
We can see your presentation. We can't see you.
Oh. There we go. Okay. So we have a couple of poll questions I wanted to ask before I start my presentation. Muriel, could you bring those up, please? So the first one is, for the attendees here, are you familiar with the SAE J2735 map messages? Just a simple yes or no on that one. And the second question is, have you created a 2735 map message? Yeah, I'm probably going to bias it because there we go. And while Muriel's coming up on that, okay. Kind of what I was thinking we might see, where 43% of you know what the map message is, but then only 13% have actually created them. And it's kind of a specialized skill. And so we'll get into this. So what I wanted to talk about during my time in the webinar is what UDOT has experienced with map messages as we've created them and used them. So since half of you understand map messages, I'll give a little introduction as to what they are, then their experience we've had with them at UDOT, are the tools and methodology we use to create map messages, our lessons learned, and the need for map guidance when you're creating these things. How can you have consistency? And the future needs that I see will be needed, not just by UDOT, but by other agencies or IOOs that create maps. So what's the map message? The message itself is defined in the SAE Society of Automotive Engineers J2735 standard. In that standard, there are lots of messages, probably about 15, 16, that are used for connected vehicles. One of those is the map message. So the standard defines what that data structure is, the map message is. The approaches, the lanes, lane geometry, lane movements. It contains detailed information about an intersection or a roadway. And this map message is what the roadside unit and also the onboard unit use to determine where vehicles are in lanes. And I look upon the map message as being a foundational piece of connected vehicle technology, because without it, vehicles have no idea where they're at on the road. So how is this map message used? So we create the map message beforehand. A team, in our case, it was me when we first started this project, in 2015. And since then, when we've hired contractors such as Panasonic and Narwhal, they've been creating map messages for us. So message is created. It is uploaded to a roadside unit, specifically the system control module. And once that map message is there, it is broadcast by the RSU once per second. The onboard unit on the vehicle receives the map messages and uses the intersection of roadway geometry contained in the message to determine where in the intersection of roadway that the vehicle is when it enters that geofence. As Ralph just discussed, how does the vehicle know when it can send an SRM message? When it enters that geofence, which is defined by the map message. So creating a map message can be kind of tedious. There are inputs that are needed for the information that's going to be used to create the JSON file or the binary file that is used for the map message that would broadcast. So in our case, the intersection data is approaches, lane IDs, lane node points, the width of the lanes, the lane movements, is it a left turn lane? Is it a right turn lane? What lane does it connect to? That's what these movements are. Crosswalks, where are they located? Signal group IDs, in our case, are also used for UDOT so that the signal control module knows what phase of the signal lanes are associated with. So all this information is put into the map, and I'll talk about the tools that are used to get this information in there in a little bit. And the outputs that we have are text or ASCII files. And in our case, sometimes they're called an nmap file, which you get into, or a JSON file. Also, some of the tools actually create the map message payload, which is a binary file, non-human readable. And that payload file, the binary, is what is transmitted through the air. So here are some of the elements that we use to create the map message. So in a tool, you can see all the green points are ingress lane nodes on the approach. And we drop these points to define what the lane does. Is it straight? Is it curved? A left turn, you can see there. And the red node points are for egress lane node points. And you can see right in the middle of the intersection, there's a blue dot. That is the intersection reference point. And that point is absolute coordinates. And the node points, based on how you encode the message, is what the offsets are for each node point from that reference point. And when we create the map message, using offsets from the reference point, it makes the map message smaller. And this is important. I'll get into that later. But this way, we're not broadcasting through the air absolute latitude and longitude coordinates, because it just, we run out of space. So all this information is input and it's done manually. A very labor intensive process for creating map messages. And the next thing is, okay, so how do you do it? So our experience with the map messages, we have over 300 intersections that we've created maps for. The tools that we used in the beginning, and occasionally I still do, is the Esri ArcMap GIS tool, where I would, I was the one who started all this out, and dropping node points on there, defining lanes, and that information was then output, saved as a shapefile, output, pulled into Microsoft Excel file. Other information was added into the Excel spreadsheet where we didn't have that information in the shapefile. I wrote some in-house developed software that would take that data from the spreadsheet, and it would pump out an nmap file, which is an ASCII file that was required for the MIT software that we used when we first started this process out of connected vehicles and intersections. Now, trying to get good aerial imagery sometimes can be a challenge. Luckily, we have a Utah Geographic Resource Center. That's part of our Department of Technology Services. And I was able to obtain from them 6-inch resolution aerial imagery that I could load into the ArcMap tool, so I could see the lane markers, get very precise node points dropped down. After this, Blaine Leonard, who's my boss, who we heard from earlier, wanted to know how accurate were our maps based on, using that Google imagery or the 6-inch resolution imagery we got from the state. And the only way you could do that is to go out there and give them a map of our node points. And our field surveys went out there, surveyed the intersection, came back, and we found out that our node points were really, really close. So we're very happy with that. And because of that, one of the challenges that we find, and what helps really when you're validating your map messages, is to do field surveys of specified intersections, not all of them, just to make sure your methodology is working. So that was the tool of the tools that I used to create map messages. And then we found out just about a year later that the USDOT had a map creation tool. And you can see that the web URL is there for if you want to see what this tool is. And what was really nice about this tool is it speeds up the process, because you can drop in all the information that is needed, lane nodes, approaches, whether it's ingress, egress, lane widths, signal group IDs. And then they have software in the tool that will create the JSON file, also an ASN.1 file, and a binary file that contains the map message. So the software that I had to write was no longer needed. We didn't need a Microsoft Excel file anymore. So very, very useful tool. There were some shortcomings on the tool, and the USDOT is working on improvements to these shortcomings, and I'm really excited about getting the new tool. So some of the challenges that we had in creating map messages, the J2735 standard can be difficult to understand. It's a very, very large document. Data formats, data structures, bit fields. And so as you're working on this, it can be a bit overwhelming. The map message creation documentation was sparse. I had to go out and search the internet for, it seemed like days and days, trying to gather information about how I can get this map message created, because in the early days of connected vehicle technology, this documentation just didn't exist. As more and more agencies were using this technology, deploying it, the documentation improved, the experiences, lessons learned, all that was lacking then. And the other issue that we've had is, what guidance should we use when we create a map message? How far should node points be? How many node points you put on a curve? And so trying to have consistent maps, at least for our state, is something that is very important. But then what happens when a vehicle travels from UDOT to Utah to Colorado? How do they create their maps? And so we found the need for a standardization of how the maps are created, not just the standards, but implementing the creation of the map. So in the beginning, we had Nmap files. Blaine discussed how we used the MIT system from the University of Arizona. And in this software, it required a file called an Nmap file. And this was a carryover from DARPA, the Department of Defense Research Group, where they created maps for roads, and it had a specified format. It was ASCII file. And so that's what the University of Arizona used. And so we had to use this. And again, it's a text file. I'll give it show you a little bit of what it looks like. So figuring out how to create this thing, what goes in this map, was one of the issues. And then creating the intersection reference point, load lane nodes, and ArcMap, as I described earlier. The imagery we had from the state was that Google imagery. I exported the reference point and lane node data into Microsoft Excel, added more information, ran it through some software I created, the Nmap file was generated. After it was generated, I ran it through another program I wrote that would validate the Nmap file to make sure that it was formatted properly, nothing was missing, and we're ready to then take that Nmap and upload it to an SCM module at the intersection. The Nmap file, after the validation, like I said, is now now ready and can be uploaded to MITS. So here's just a screenshot of the Esri ArcMap tool that was used to create an intersection. And you can see here, again, the green dots are the lane nodes of the ingress lanes. The red are the lane nodes for the egress lane. And here in the center, you can see a yellow dot. That is the reference point of the intersection. And all these points were created in ArcMap, saved in a shapefile. And then that shapefile, I also exported the information to a tab delineated text file that could be then imported into Excel. So you can see it's pretty labor intensive to get all this in there. And then this is an example of what the Nmap file looks like, just a portion of it. You can see here the intersection or the map name file that is going to be uploaded to the SCM, the RSU ID, intersection IDs, again, lane nodes, approaches, all the nodes. So that's what, after creating the information in Esri, downloading or exporting the data, taking the Excel sheet and adding more information, or running through the processors, this is the final input. This is the file that can then be loaded to the signal control module. So the USD map message building tool, again, it allowed us to build map messages much faster. And a lot of the headaches, a lot of manual labor just went away. And the output is a JSON file, which is very similar to the Nmap file, and a binary file, which is the actual payload of the map message. And they also have a map message validation tool that you can run your message that created, you can run the map message that was just created through the validation tool, very similar to the software I created, and it makes sure that the map message came out, nothing is missing. Here is an example, a screenshot of the USD map tool and the intersection that was created, and the lanes. And again, you just drop this in through their graphical interface and then spit out the data. Here's an example of their JSON map file. As you can see, they've got the intersection data, very similar reference points. Here's your first approach. So through the years, as we have created map messages, we've found some issues that have come up. The biggest one by far is when you're trying to create a map message for an intersection that's under construction, it's being ripped up. They're adding curb and gutter, they're changing signals. And so the imagery that you have doesn't match what they're doing on the ground. Or when they finally finish, it's not going to match what the imagery is on the ground. So you don't know where your lanes are, or where you're supposed to put the lane point, the nodes. It's kind of a guessing game. The other issue is having aerial imagery that is out of date, or the resolution is poor. So again, you may have intersections that have been changed, but the aerial imagery just doesn't contain these changes. The other issue is making sure that the map message is accurate, that the lane nodes are where they're supposed to be. Are they really on the roadway? Are the coordinates valid? So here's an example of road intersections under construction. So Blaine mentioned in Provo, Utah, we have the Utah Valley Express UVX line. And when I was creating map messages and I brought up the imagery from that I had from the state. This is what I've got. You can see the road is ripped up. So no lanes, what am I supposed to do? So in this case, I was able to get to the engineers who designed the road to get their intersection plan sets. And from here, you can see where the new lanes are going to be, curb and gutters, crosswalks, all that information. That's great, but how am I going to get that overlaid so it'll be useful for me? So I was able to take these files were in MicroStation, and they could export a KML file. The KML file was then loaded into ArcMap as another layer. And you can see how the lanes look here based on the plan sets. And from here, I was able to create node points, crosswalk information that is accurate. After I was able to go to a few intersections after the imagery was actually reshot with the new intersections after they'd been constructed, and I could see how good I did or how poorly I did. Most of the time, I was pretty good. Sometimes I was off a little bit and I needed to correct some of the intersections. So what kind of lessons did we learn here? When you're first starting out, good informative documentation is a must. I spent a lot of time just trying to learn how to create map messages. And a lot of these issues have been resolved with the USDOT's map tool, because it does a lot of this automatically for you. Just drop it in, put the information in, and it spits out what you need. But in the originally starting out, it was just difficult to find information. Better documentation would have solved these problems and lessen the learning curve on how to create these map messages. Another issue is the payload size of map messages is around 1,450 bytes. This limitation, when I first started creating intersection maps, I didn't know how far I was supposed to put the lane nodes, so I just started dropping them every 50 feet. And once we hit large intersections, suddenly we exceeded that minimum or maximum packet size. Again, this is where guidance would help. So after trial and error, I realized that I should put these node points as far apart as possible. I realized there was another limitation in the standard itself, that you could only have nodes 328 feet apart because of the size of the byte size that they were using. Another issue, computed lanes is another feature that is in the USDOT's mapping tool, where you can reduce the number of your lane nodes because the lanes can be created automatically. That helps. Another problem is curve. When you start dropping node points on curves, you have to put a lot of points in because the chord line between the points on the curve will miss. It'll go outside of the roadway if you do not put the node point close enough. And again, more node points mean larger packet size. So that's an issue. The manual workflow process has given us insight into how the process be sped up, and using software, USD's DOT tool has helped. How can you automate many of these tasks and create map messages? And that's an ongoing task. The other one that we learned is when you have intersections under construction, how do you get up to the information? Again, you saw how I used the plan set, but also we had some lanes restriped on Redwood Road that Blaine mentioned earlier, where they went from 3 lanes to 4 lanes. And we were able to have UDOT survey crews take their drone up, take imagery and survey endpoints. So I could then use that kind of imagery. That's, current, right then, exactly what we needed. So one of the, I'm going to put plug in here for the Connected Vehicle Pool Fund Study map guidance document. This was a project that Blaine wanted the pool fund study to do, because based on the experience we had, and all the issues that I had creating these things, is there needed to be some guidance on creating documents. I've been the project champion for this since it started. It's turned out to be a very, very good project. We took a lot of input from many people in getting this document put together, and you can see the guideline or the URL where you can obtain it. I'm just going to give it, the document's 103 pages. We got a lot of figures, a lot of guidance statements. Here you can see the 7 steps. Kind of running out of time here. I want to answer some questions from people. But in here, all this is in the document. You assemble the data, how you create a map message, field validation. And here is some of the guidance sections that we have held this information. And this was the kind of information that I needed when I was creating the maps. How far do we put those node points? What's the actual need? Where do we start the first node point of a lane? Is it on the stop bar? Is it at the crosswalk? All this information that we gathered from interviewing many agencies is in this document. And what are our future needs? Best practice guide for creating map data. So we have the map guidance document, which has become extremely valuable. This document was given to Narwhal and Panasonic, and they used it when they've been creating map messages. A methodology for automating the map message file creation needs to be improved because it's such a labor-intensive process. Validation of map messages. Right now, the Connected Vehicle Pool Fund Study has a project called SIMS underway, Connected Intersection Message Monitoring Systems. And part of this project is, as it receives map messages, BSMs, SPAT messages, it is validating this information, that the actual data that's being thrown, broadcast into the air. And we've already had one of our intersections come up and let us know an issue with our maps that we'll be fixing. So that's one way to validate this. You need up-to-date base maps and aerial imagery. And RTCM corrections that Ralph talked about are vital for making sure that vehicles are in their place in the lanes and they know where they're at. And Narwhal is going to give a more detailed information about the RTCM messages and technologies that we use. And I think that's it. So thank you, everyone. I appreciate the time to pass on this information. Thank you, Muriel.
Yeah, thank you, Chuck. Perfect. So let's go ahead and bring all of our presenters back for a discussion with our participants today. We have a dozen questions in the Q&A feature. Unfortunately, due to time constraints, we will likely not get to all of these. But please note, we will follow up via email directly with each of our participants who've had a question, and all of the answers to these questions will be posted on a Q&A matrix on our website within 1 week. So the first question, I'm going to kick it to Blaine first. It comes from Alan Toppin. Alan asks, have any automakers indicated they have plans to offer CV technology in their vehicles that's compatible with Utah's system?
Thanks, Alan. That's a great question. Several years ago, Ford announced that they would put CV2X equipment in all of their vehicles in North America and deploy those. They haven't yet done that, and the deadline they set when they made the announcement has been passed. I will note that the last several years, we've had a lot of regulatory uncertainty with the Federal Communication Commission, which has caused the automakers and a lot of others to sort of hold back temporarily. I believe, this is just me, I believe that Ford will move ahead with that commitment at some point in the future. And there are other automakers who are working in this space actively, but haven't made any formal commitments. They aren't building specifically to the Utah deployment per se, but they're building their systems and anticipate building their systems to meet a set of national standards, as are we. And so we're hoping that all of us around the country will build to these standards, and the automobiles and the rest of us will all be able to talk together. We do have an active project going on with several of the automakers where we are testing some of our intersections and making sure that we meet the standards that are expected, and the automakers are involved so that they can give us feedback about those and help us in cases where we're not meeting the standards, help us to get there. So there is some active coordination going on between us and them.
That's fantastic. Thank you for that explanation, Blaine. The next question is for Scott. Scott, you said that the antennas of the RSUs are to be ensured to not interfere with existing radios. Can you describe how you did that investigation?
I'm actually not too familiar with any kind of formal investigations that were performed on interference testing. Maybe some of the other panelists have some additional input to that. But I will say, I think this goes back to what Blaine mentioned earlier, which is, part of the knowledge we've gained is just try it and start small. So, we've put these devices out into the field. We've done it at, just limited sets of intersections and vehicles. And we actually opened risks, in the project to be ready in case we did experience some interference, that we could go address that. But fortunately, to date, we haven't really seen any issues with that. And it's a little bit of a trial and error approach. I don't know if Blaine or Jonny, any of you guys would add anything to that.
Yeah, I'll just chime in there. Antennas have their radiating pattern and their interferences between different spectrums. And so that just gets looked at. We looked at the Smith charts and things to see what their radiating pattern is and things like that. But like Scott said, a lot of it's just in the field testing, making sure that, we're not seeing it. And to date, we really haven't seen much in the way of issues. The bigger issues that we've seen are that you need to make sure you have a ground plane. Some of the vehicles like buses have a fiberglass lid, so you need to make sure that you have a ground plane on that antenna because you're not getting it from the vehicle. And so there's some details to look at for sure.
Ralph, would you like to add anything there? No. Perfect. Well, a follow-up question related to this topic comes from John Yu. John asks, are the RSP and OBP necessary? Isn't this equipment already integrated into the RSU and the OBU?
Yeah, so that's a great question, John. So the roadside processor came about because of some of the institutional requirements of Utah DOT, not wanting to put additional processing power into the demands on the signal controller. So SPAT, how do you generate SPAT? At the time, there was no way to do that on the RSU. Same thing with the on the OBU side, when this was initially deployed, there was no way to generate SRMs on OBUs. So there is capability to do that now without having an OBP or a signal command module at the roadside. But for things like RTCM, we're not aware of any OBUs that can do RTCM correction on the vehicle side. So in that case, an OBP is still required as far as we're aware.
I will quickly add that although in many cases we could install this software on the RSU or the OBU, we're using multiple brands of hardware, and rather than customize the software for each platform, having it on the OBP and the signal command module allows us to have the software be consistent.
Fantastic. I think we're going to need to leave it there with participant questions for today. And I'd like to give each one of you about 30 seconds to highlight one key takeaway that you'd like our participants to come away with today. We'll start with Blaine, then Chuck, Scott, Ralph, and Jonny.
I would encourage everyone to get started with this technology.
I think if you're going to create maps, become familiar with the ISD tool. They are working on a new version, and they've taken a lot of input from users. And the next one is use the Connected Vehicle Pool Fund Study Map Guidance document. It'll make your life a lot easier.
Yeah, I'd say in addition to getting started, just make sure that you get relevant stakeholders involved as early as possible in the process. That'll really help to make sure you're developing the right solution that fits their needs.
In the poll that I had, I think there were about 30% of respondents that had already deployed V2X. I just want to say congratulations to you. I forgot to do that. And for the 63% or so that are still investigating that, follow Blaine's advice and just get started. Take small steps.
Yeah, and I would echo that, and as well say, having worked in ITS my entire career, be prepared to grow and really have a great sense of satisfaction of doing real, I don't want to scare anybody by saying really hard things, but, ITS developed a lot and in my career and went from being, a harder to work with system to being more streamlined, and we're kind of at the beginning of that with V2X, and that sense of satisfaction and growth you'll definitely feel as you get involved with this technology.
Fantastic advice, gentlemen. We will leave it there. To our participants, thank you so much for engaging with us today. We will be in touch with the follow-up materials that you heard today, and we welcome your participation in our next 3 webinars. Thank you.
Thank you.
Bye now.